Hi everyone, this is Rumesa. I will present our work on 3D dense geometry guided facial expression synthesis by adversarial learning, which is a joint work with Binod Batari and Taekyun Kim. The change in expressions is caused by geometrical actions of facial muscles. We can observe from the figure that there are fine detailed changes of facial muscles between expressions. To address such a fine-grained problem, optimizing existing loss functions or adding a target attribute classifier on the discriminator side is not enough. Some existing studies propose to incorporate geometric information with landmarks or action units. However, these annotations are sparse in nature and, as seen from the figure, cannot capture expression-specific fine details such as wrinkles on the cheek, forehead, and the shape of nose and eyebrows. Unlike sparse annotations, depth and normal maps are capable of capturing these geometric clues. There are some facial expression datasets that consist of depth and RGB pairs, but they contain limited number of expressions or samples and are obtained in a controlled environment. To the best of our knowledge, there is no publicly available large-scale dataset in the wild with expression and depth annotations. We propose a null geometric consistency loss to guide the expression synthesis process using depth and surface normals information. We construct a dataset that consists of facial images and their corresponding depth and normal maps, which we obtained using a 3D reconstruction method. We propose a null regularization to penalize the confidence of the depth estimator to improve generalization. We compare the proposed method on two challenging benchmarks. As there is no large-scale dataset available which fits the requirement to train again adequately, we utilize a publicly available model to reconstruct 3D meshes of the images of EffectNet and RefD. We manually discarded 3D meshes that are poor in quality. We project the reconstructed meshes and interpolate missing parts of the projections in order to acquire the corresponding depth and normal maps. The table shows the number of images obtained by this process. We pre-trained the depth network that estimates depth maps from RGB images on the dataset that we constructed. We train it with strong supervision than prior so that it can generate reasonable depth maps for given synthetic inputs during the end-to-end training. Since we have paired data, we employ a pixel loss and a perceptual loss along with adversarial classification and reconstruction losses, which are also used during the end-to-end training. To improve the generalization of the depth network, we use a negative entropy as a confidence penalty. Here are real test images with their corresponding ground truth depth maps and the depth maps predicted by our depth estimator network. We can see that the depth maps are aligned with the geometry of real images, and our network is able to preserve the geometry. We propose to train two types of adversarial networks, namely RGB and depth, in an end-to-end fashion. This part of the pipeline describes the RGB adversarial network that consists of a generator and a discriminator. The network takes as input an RGB source image along with its target expression label as condition. gRGB translates the source image in the guidance of the given target label, and dRGB ensures a realistic look in the target domain and guides gRGB to generate images that can be confidently classified as the target expression. Consisting of the adversarial, classification, and reconstruction losses, the overall objective to minimize for the image network can be seen on the bottom left. We can see that none of the objectives are explicitly modeling the fine-grained details of the expressions. Thus, the solution from RGB network alone remains suboptimal. To address the limitations of this network, we propose to append the aforementioned pre-trained depth network which operates on the depth domain and guides the RGB network. Depth maps are able to capture the geometric information of various expressions. As seen in the figure, the depth network also consists of a generator and a discriminator. gDepth takes as input the image generated by gRGB and generates the estimated depth map, which is then passed to the discriminator. The losses used for the depth network can be summed as seen on the bottom. The datasets used for pre-training of the depth network and joint training of both networks are EffectNet and RefD. In order to quantitatively evaluate the generated images, we compute the threshold inception distance for the generated images as well as the peak signal-to-noise ratio and the structural similarity between the original and reconstructed images. We further evaluate our method by applying an expression classifier that is independent of all models. We compare our method to some of the state-of-the-art attribute manipulation baselines, StarGAN, Ganimation, and Gantation. The latter two utilize geometric information, and StarGAN is our baseline which corresponds to the RGB network of our pipeline. However, our method can be extended to other baselines too. As seen from the table, our method yields a 5.1% improvement over the baseline by reaching 87.2% on EffectNet and an 8.9% improvement with an accuracy of 62 on RefD. The FID values decrease for both datasets, indicating better image quality and diversity on the synthetic images. Our method also improves the PSNR and SSIM scores that evaluate the reconstruction performance of the networks. Here is a comparison of samples generated by the baseline and our method along with their predicted depth maps. Our method synthesizes the face with a realistic geometry, whereas the baseline results in artifacts, particularly in areas like mouth, nose, and cheeks. The predicted depth maps verify this inference. Our method is also capable of providing photometric consistency. Images synthesized by the baseline contain